So what is a simple linear regression? Simple linear regression is used when we want to make predictions about a continuous dependent variable, which in regression is also called an outcome variable, based on one independent variable, which in regression is also called a predictor variable. This is a parametric test. And so this means that the residuals assume normality. This is a little bit new for our workshop series. Normally when we say normality, we're not talking about the residuals, but we'll cover this in more detail. So we're looking at our residuals and they should form this typical bell-shaped curve. If you are looking for additional help running a simple linear regression, there is the University of Guelph SPSS LibGuide, the Laird Statistics Guide, or the SPSS documentation where you can get a little bit more support. What are the assumptions of a simple linear regression? We have 7, and we're going to cover all of them today. The first is that your outcome or dependent variable must be continuous. The second is that your predictor or independent variable should be continuous, approximately continuous, which is some ordinal data if you do some data wrangling, or it must be dummy coded if you've got a categorical variable. The third assumption is independence of observations. The fourth assumption is there needs to be a linear relationship between your variables. This is sometimes called linearity. And then our last 3 assumptions all have little stars, which means we do the regression first, and then we check these after we've built our regression model. So our 5th assumption is homoscedasticity, $5 word. Our 6th assumption is normality of the residuals. And our 7th assumption is no significant outliers in the residuals. Okay. Side note, it is possible to do simple linear regression with a categorical predictor variable. It's not as easy to accomplish. So I've left you a resource on the slides about dummy coding your variable. I think our example today is a continuous example, but I think our example next week, I think I've got 1 continuous and 1 categorical. So if you're confused about dummy coding, come to the workshop next week where we're talking about multiple linear regression. All right, let us begin. Our first assumption is that your outcome or dependent variable must be continuous. So if we use, for example, fake data 1 in our data set, we can look at this, we see a range of values, we see a bunch of decimals, we can say, yep, this looks like it's probably continuous data. So we have passed this assumption. Our second assumption is that the predictor variable should be continuous, approximately continuous, or dummy coded if it is categorical. Here we're going to be looking at fake data 2. We can look, we see a range of values, we see some decimals. It's a giveaway that this is probably continuous data, which means we've passed our second assumption. The predictor variable in this case is continuous. Our third assumption, we normally set this up before we actually get to this stage. So if you're doing a survey or an experiment, you normally make sure your data is independent at that stage. But we can look in each row of the data and say, does this look like a unique participant? So for example, row 1, we've got someone who identifies as male. They have data for fake data 1, fake data 2, fake data 3, and fake data 4. They've got a colored piece and they've got a group piece. It looks like each person here is a unique participant. It's hard to tell after the fact, but it's all fake data. We can say that this assumption passes today. Reminder, you normally set this up before you do the study. You want to make sure you've got unique data for each participant. Our next assumption is called linearity. You must have a linear relationship between your variables. So here, if we've got a continuous predictor variable and a continuous outcome variable, we want to make sure that they look like they have a linear relationship. To check for linearity, the easiest way to do this is to actually click Graphs and Chart Builder. So what we're going to do is we're going to create a scatter plot of our 2 variables to say, does it look like a straight line? So if you click Graphs and Chart Builder, you will likely get a pop-up. It's asking to make sure you've ensured your data types are set up properly because you've got the fake data from me. They're both set up as continuous or scale data in our variable view under the measure column. So we can say OK or continue. We're good. Our data is set up properly. So chart builder, say OK, and then you'll get your chart builder dialog box, which looks something like this. The easiest way to look for linearity is a scatter plot. So in the bottom left, we're going to click where it says scatter/dot. The dialog box is a little weird to use if you haven't used it very much before. You grab the first plot option. It looks like a bunch of blue data points, and you drag and drop it to the blue text in the middle of the screen. And then what happens is it pops out like some fake data points, so it makes it look kind of like a scatter plot. That means you've picked the right one. What you do next is you grab your 2 variables, fake data 1 and fake data 2, and you put them on your X and Y axes. I think I put fake data 1 on the Y and fake data 2 on the X here. And if you've done that, it populates some fake data. It doesn't like more fake data, not our exact fake data. It populates just like what this might look like if you built this as a graph. It should look like just a bunch of random scatter plot points. If it looks like what mine looks like on the screen, you're good to go. You can click OK. So you just have to make sure you click scatter/dot. You move the graph that you want, you select your axis options, and then you're good to go. If you do all that, you'll get a scatter plot that looks something like this. You'll have blue points. I made mine red to match the presentation. So we have fake data 1 on our y-axis, and we have fake data 2 on our x-axis. And what we're doing here is we're looking at this critically and saying, does this look like it forms a straight-ish line? If I was to draw a line through my data points to try to touch as many of those data points possible, does it look like a straight line? It can go up, it can go down, it can be going kind of flat. Any of those are fine, but it should be a straight line. This is a tricky example because if you were to split this plot in half, it looks kind of like the left side is going down and it looks kind of like the right side is going up. So it almost looks a bit like a V. So it's a little tricky. There's something that we can do to help us visualize, is it a line? If you double click on your plot, it will open up your chart editor dialog box. So it should look something like this. So if I double click on the plot, it'll open up another box for us here. And there's a button that we can click to add a line to our plot for us. So it's this button right here. There's 2 rows of buttons in SPSS in the chart editor. It's on the bottom row. It's one of our last buttons. It's literally a little XY axis with a straight line through it. If you click that, it gives you a few options that you could select to add a line to your plot. The default is, I think it says linear or line. That would always give you a straight line. So every single time you do it, it gives you a straight line and says, here's where your best fit is. It's the line of best fit, a straight line. You could select that. The option I've selected is actually called a LOESS, LOESS. Some guides will refer to this as LOESS, LOWESS. They mean the same thing. So we can actually add a LOESS curve. It's essentially, I'll break it down. I'll explain what it is. It's essentially, for example, taking your first 5 data points and then drawing where the line of best fit would be for that. Then it moves over by 1 point. So it would take points 2 to 6, and then it would draw where would my line be. Then it moves the window. So it would do lines or points 3 to 7, and it would draw where's my line of best fit. So it essentially is doing your line of best fit for different chunks of your data all the way through and saying, here's what it would look like for each of those chunks. So the LOESS curve here, it's not just a straight line. It's using pieces of the data to say, for just these pieces, what's happening with my line? And as you move that window, the line could change. It might not always be a straight line. So if we had a LOESS curve, we can look at this and say, does this look like a straight line? Well, on the left-hand side here, it looks like it's mostly going down. And on the right-hand side here, it looks like it's mostly going up. This part is quite straight, like very surprisingly straight. But the stuff on the left is not really a straight line. So we could use something like a LOESS curve to help us determine, is this a straight line? Do we meet the assumption of linearity? In this case, it's a little rough. If I looked at this on some real data, I'd say you're maybe okay, but you would maybe be concerned that you've not met this assumption. So it's a reminder to always check your assumptions. You don't know if you've met the assumptions until you check them. So tricky to say. It's possible we passed, or in some people's eyes, maybe we failed this one. Okay. What we do next is, assuming you've passed all your assumptions, we can proceed to conducting the simple linear regression. And you might be going, Lindsay, what's going on? There were 7 assumptions. We have not covered 7 assumptions yet. 3 of our assumptions, you build your regression first, and then you check the assumptions. So if you've passed the assumptions so far, now is when you would do the regression. And you do that by clicking Analyze, Regression, Linear. This is an example where SPSS has made it super easy to find what you're looking for because it's actually using the name of the thing we're trying to do. So there's 3 assumptions we still have to check. So what we're going to do is run the regression as normal and then check our last 3 assumptions. So if you click Analyze, Regression, Linear, you will get the linear regression dialog box. What you do is you take your continuous dependent variable, also called your outcome variable, and you put it in the box that says dependent. and it should have a little yellow ruler next to it saying that it's continuous data. You can also take your predictor or independent variable from the left-hand side and move it to where it says independent or independence. The trick here is this might be a little yellow ruler if it's continuous or approximately continuous, or you might have that little bar plot. It's got a blue line, a green line, and a red line if you had ordinal data. But today we're going to use a continuous data point. So we're going to use fake data 1 for dependent, fake data 2 for independent. There's a few other things you have to do. So you're going to click the statistics box. If you click the statistics button, it will open the statistics dialog box. And you're going to make a few selections. You want it to say estimates, confidence intervals at 95%, that's default, model fit, and descriptives. When you've done all that, you click the continue button. Just pausing for a second in case anyone's doing that. There's a few buttons here. Once you've made your statistics selections, you're going to click where it says plots. This is to check one of our assumptions. You're going to take where it says Z-pred or Z-predicted, and you're going to drag and drop that to where it says X. You're going to take Z-resid, also known as Z-residuals, and put it where it says Y. So Z-residual on the Y, Z-predicted on the X. You should also have histogram and normal probability plot selected in the bottom left-hand corner. Once you've done that, you can say continue. This will make a plot for us to look at. You also want to click the Save button. This will open up our Save dialog box. It's important that we do this because this is for our assumption of normality, and I think also outliers. So we want to say standardized residuals. It's kind of near the top right. What save does in SPSS, anytime you click the Save button, it means you want to save a column of data, or more than one if you select more than one option, into your data window. So it's going to create a new column for us, and we're going to use that column in a few minutes. Once we've said standardized residuals, we can say continue. And that's everything we need to do. If you've made your selections in statistics, plots, and save, you can click the OK button. You're ready to run the regression. Okay, if you have made all of those selections, you should get a pretty big output file. There should be quite a bit going on. You're going to scroll down to the scatter plot it just generated for you. Hi, this should look a little bit familiar. It's made you a scatter plot with your standardized residual and your standardized predicted value, because we said in the plots, this is what we wanted to generate. So now that we've built our model, we can check our assumption of homoscedasticity. What we're looking for here, this is called a residual versus fitted plot, the scatter plot. We want to see no obvious pattern. There should be an approximately equal number of points on the top half and the bottom half. There should be an approximately equal number of points on the left half and the right half. There should be no obvious cone or fan shape. So if you were to draw a sideways V, you don't want to see the points following a sideways V going in one direction or the other. If I look at this, it's got a little bit of a U going on, but approximately equal top and bottom, approximately equal left and right, no obvious fan or cone shape. We get a thumbs up. We have passed the assumption of homoscedasticity. More assumptions. We have to check for normality and outliers. You've seen this before if you've come to any of my workshops, but now we have a new column of data that we're going to use. So we have to click Analyze Descriptive Statistics Explore. But in our data window, we have a new column because we build the model first. We get our standardized values, and then we use the standardized values for this check. So Analyze Descriptive Statistics Explore. That will open up the Explore dialog box. And we're going to take this ZRE_1 option and put it where it says dependent list. If you were doing multiple regressions on the same day in the same window, you might not have ZRE_1. It'll just increase the number. So if I do 3 regressions in the same day, I'll have ZRE1, ZRE2, ZRE3. So you want to pick the one that is for the regression you just ran. So today we only have one of them. It's really easy. It's ZRE1. So we're going to take this and put it in dependent list, and then we have to click the plots button. We want to uncheck stem and leaf, check histogram, and check where it says normality plots with tests to make sure we're checking for normality and outliers. Once we've done all that, we can click the continue button, and then we're good to go. We can click OK. So if we make these selections in the Explore dialog box, in our output, we can check for normality and outliers. We're checking our residuals. ZRE1 is our standardized residuals. We can scroll down to where it says tests of normality. If you have 50 or more observations, you're going to look where it says Kolmogorov-Smirnov. Here we have fewer than 50 observations. We're going to look on the right-hand side where it says Shapiro-Wilk. If P is less than 0.05, it means you have a problem with normality. You have failed the normality assumption. It might not be appropriate for you to run this test. Here we have a p-value greater than 0.05, which means we're okay. We've passed normality. This is how to check normality with statistic. We can also check normality using some histograms. We actually have two versions of this histogram in our output right now. If you've selected everything I've selected, you should get one from the Explore procedure, and you should get one, I think, from actually just running the regression as well. So they both look about the same. One of them has the literal line for a bell-shaped curve imposed on top. But for both of these, we're looking to say, does it look like our typical bell-shaped curve? And for both of these, I'd squint and say, yeah, that looks pretty good. We've passed normality. For visual inspection, we can also look at our QQ plot. It's got a straight line going across the page and a bunch of data points. We're looking to see, are the points on or pretty close to the line? Here, I would say, yeah, that's a pretty good QQ plot. Everything is close to or on the line. I would say with our statistic and our two kinds of plot, we have passed normality. Excellent. At the bottom of the output file, we should see our box plot. There are multiple ways to check for outliers. This is one way. SPSS makes the box plot method really easy. We've got our median, our interquartile range, and our whiskers, and we're looking to say, are there any data points outside of those whiskers that might be considered outliers? If it's a circle with a number, it says that that data point is an outlier, and it's telling you the row in your output that is the outlier. If it's a star with a number next to it, it's an extreme outlier, and the number tells you which row is an extreme outlier. So here we see no outliers. So we've also passed our assumption for outliers. We have checked all of our assumptions. We've maybe failed linearity, but everything else looks okay. Let's proceed and actually look at our regression, which you would do if you've passed all your assumptions. Okay. The regression output. There's quite a bit here. I'm going to show you just the most important pieces. So in our model summary table, this is telling us how good of a job are we doing? How good does our predictor do in actually saying what is happening with our outcome variable? So here we look at our R-squared value, and we can see a value of 0.008. If you multiply this by 100, it will give you a percentage. So here we are sitting at 0.8% of the variance of our outcome measure is being explained by our predictor measure. So not very good, less than 1%. We can also look at the ANOVA table. And this, in the SIG column for the ANOVA table, will tell you essentially, is this doing a good enough job? Our R-squared value is very low. Our predictive power is pretty low. And our p-value for ANOVA is non-significant, p greater than 0.05. This is saying we're not doing a super great job. So we would actually stop here, and we would not move on to actually interpret our linear regression. Because our ANOVA is non-significant, we would stop. If your ANOVA value, your p-value here, was less than 0.05, that'd be, yep, you're doing a good job. You're allowed to interpret your regression. For practice today, we're going to interpret our regression anyway. But normally, we would stop right here. Oh, and I've got some circles. So R-squared, this SIG value. The coefficients table, which is your next table here, is your actual regression proper. So this is your linear regression. There are two super important pieces of this table. The rest of it, it's important too. You'd probably report it in a paper, but less important if you're like, I just want the quick and easy version. So the constant line, if you remember from like high school math, if you ever did y equals mx plus b, the constant line is your plus b. This is your intercept. You generally ignore the constant line unless you were trying to build a regression equation to help you predict something. Most people, when they come see me, they actually just ignore the constant line because they're not building an equation. So that's okay. We want to look where it says fake data equals 90. This is our fake data 2 variable. So this is our predictor variable. We want to see how well is our predictor variable doing at explaining our outcome variable. We can look where it says SIG. This is our p-value. Hey, these two match because it's a simple linear regression. It's not doing a good job. Predictor, our fake data 2 predictor variable is not doing a good job explaining what's happening in our fake data 1 variable. And that's okay. That's real data. It happens sometimes. So we would not continue to interpret this again because this is non-significant and it matches this ANOVA. So we already would have stopped because it's non-significant. If our p-value was less than 0.05 here, we'd be able to say that our predictor variable here, fake data 2, is doing a good job at explaining something that's happening in fake data 1. And we'd be able to interpret this and say, how good of a job is it doing? We can quantify how much variance is being explained by looking in our unstandardized coefficients section in this beta column. So we would look at this value here. So again, we wouldn't look at this today, but if this was significant, we'd be able to say for each 1 unit increase in fake data 2, our predictor column, we're seeing a 0.061 unit increase in our fake data 1 column. Because this is a linear regression, you could also say a 6.1% increase. It just so happens that 6.1% is actually not enough for it to be significant today, and that's okay. But we'd be able to say, with all of the data on the screen, less than 1% of our variance is being explained by our predictor variable. It's not doing a very good job, so we would stop. But if it was doing a good job, we would look in our single row here to say, what is happening? What's our significance for that variable? And how much is being explained? Here, 6.1%, i.e. for each 1 unit increase in our predictor variable, we're seeing a 6.1% increase in our outcome variable. That is how you run a simple linear regression.